Now it's time to take a look at another important aspect of understanding electricity: wiring methods. As we just saw in the previous section, there is always an alternate way to approach wiring within the home. The particular wiring approach taken in your home will depend upon when it was built and what the approved methodology was at that time. Here's what I mean. In this graphic, we have a wall switch controlling a ceiling light. With this view, we can't tell how the wiring is connected. But in this next graphic, the key detail is provided. This is a wiring pattern of an older home. We know this because at the time this home was built, the trend was to run the power from the service panel into a ceiling junction box and use a separate cable to control on-off switching. Today, the current trend is to run power to the wall switch junction and then run a separate cable to the ceiling junction for the light or ceiling fan. A different wiring method than the previous, and both approved by the National Code. So depending upon the age of the home, you could encounter either one. Now the question is, does it make a difference? The answer is yes, and here's why. Seen here is the actual wiring for the power to the ceiling junction method. As you can see, the hot wire from the service panel is spliced to the cable going to the wall switch, black wire to black wire. However, the white wire coming from the wall switch cable is energized whenever the switch is turned on, and for me, that's the item of concern. By code, the white wire is the neutral wire in every circuit. It is a standard we rely upon. Yet here, when the wall switch is in the on position, the white wire becomes the power feed to the ceiling light. It becomes the same as a black wire. If you didn't know this, you could touch the white, believing it to be a neutral, and possibly be electrocuted as a result. It's a foreseeable problem. And to answer that issue, the National Code specified that in this situation, the white wire had to be marked as a hot. To do that, a piece of black electrical tape is wrapped around the wire as a notification. This must be done within each junction box where a person could encounter it. And because of this, the first rule of opening up an electrical junction is to stop and observe the wiring. Look for the visual notifications before proceeding. And if you open the wall switch junction and there is only one incoming cable, that's the first clue that this home was wired following the older wiring method. Today, the method applied is different, as seen here. Here, the power from the service panel is run to the wall switch junction. A separate cable runs to the ceiling junction. At the ceiling junction, wiring follows the NEC standard: black to black, white to white, ground to ground. It's the same in the wall switch: black to black, connected through the switch, white to white, and ground to ground. Clear and understandable. Replacing the wall switch is a relatively simple task. The switch may be broken, or you may want to upgrade it to a more contemporary decorative rocker switch. Here are the steps to follow. Step 1. Identify the branch circuit feeding the switch and turn off that breaker in the service panel. Step 2. Remove the cover plate and undo the outlet screws, allowing the outlet to come free of the junction box. 3. Observe the wiring inside. There may be more than one circuit running through the junction, and if so, there may be live wires present. The two wires connected to the switch are your focus. Use your test meter, verifying there is no power standing on either wire by holding one probe against the ground wire in the box and the other to each screw on the switch. The meter must read 0 voltage. Once verified, it is safe to proceed. Step 4. Disconnect the old switch. The wires on the old switch may be connected using the side screws of the switch, or they may be inserted into the push connectors on the back. To release the wires from the push connector, insert a thin blade into the release slot. While applying pressure inward with a blade, pull the wire out. It sounds simple, but I don't find it to be all that easy. First of all, I think it takes 3 hands. One to hold the switch steady, one to push the blade in, and a third hand to pull the wire out. Honestly, I don't waste time on this. It can be a battle and not one worth fighting, especially if you're tossing the old or broken switch away. There is usually enough slack in the wires that you can cut the wire against the switch and move on. And if not, you can always splice on extra wire to make up for it. Here is the replacement switch. The new switch is surrounded by a metal support bracket, which means it will also have a ground wire connection point. It is my recommendation to connect the ground wire to the switch. However, I acknowledge that not everyone follows this practice. They think it's just a switch and doesn't need grounding. I disagree. If the device has a ground lug, then connect the ground. It's there for your protection. To connect the ground wire, loosen the grounding screw on the switch. Using the long-nosed pliers, bend a hook into the end. Wrap the hook around the screw in a clockwise direction. This forces the wire tight against the screw as you turn it. Tighten the screw down firmly. Step 5. Connect the wires to the switch. Strip about 1/2 inch of insulation from each wire. There is a wire strip gauge imprinted on the rear of the switch to help you. In this example, the exposed conductor is too long. We use the gauge as our guide to trim it down for a proper connection to the switch. If for whatever reason you need to connect the wires to the side screws, insert the bare portion of the wire behind the screw plate as shown here. Then screw it down tight. As long as it's a tight connection, you're good to go. Otherwise, the push connector is the simplest connection method. Insert the wires into the push connector. Push firmly, then give it a tug to be sure they are locked in. But before putting everything back together, you should test the switch. Restore the breaker to service. Then, being careful not to touch the exposed screws on the side of the switch, test your work. Turn the switch on and off. The light should go on and off. Also, note the switch orientation for on and off for installation back into the junction box. Turn the breaker off once again and reinstall the switch. Replace the cover and turn the breaker back on. You're done. Next, we'll go over how to replace a standard outlet. For the purpose of this example, we'll pretend the outlet is actually defective. Replacing a standard household outlet is another simple and easy task. The steps for doing so are nearly identical to those of replacing the wall switch. Since we just covered the wall switch, I'll move a little quicker here. Always, the first step, turn off the power to the outlet at the service panel breaker. Remove the outlet cover screw. Then undo the screws attaching the outlet to the junction box. Carefully pull out the outlet and observe the wiring to be sure you recognize everything and understand it. This one tells us a lot about how the outlets are wired in this room. First, there is a single breaker for all the outlets in the room, and there is a single cable feeding power to this outlet. That tells us the room outlets are daisy-chained together, and this is the end outlet of that chain. Before going further, use the multimeter to verify no electricity is present. Set the meter for volts AC, and place a probe against the screws for the white and black wires. With no power present, it is safe to proceed. The next step is simple and fast. Cut the wires close up against the outlet. Don't waste time trying to undo the wires. You're throwing the old defective outlet in the trash. Strip 1/2 inch of insulation from the black and white wires. There is a strip cage on the back of the new outlet, just like there was on the switch. Reattach the ground wire, creating a small hook and wrapping it clockwise under the screw. Tighten firmly. Insert the black and white wires into the appropriate push connector on the back of the outlet. Remember, the black wire connects to the side with the brass-colored screws, white to the side with the silver screws. Look at the back of the outlet if you're not sure. It should be imprinted with the word hot on one side and an arrow to guide you. Make sure the wires are attached firmly. Reattach the new outlet to the junction box. Next, restore power to the outlet and use your tester to verify your work. In this case, I'm using my handy tester. The green light should be on, and the red and yellow lights should not be on. Check both outlets. Put the cover plate back in place, and the job is done. A note here. If the junction box has 2 cables in it, that would indicate that this junction is part of a daisy-chain string, powering not only this outlet, but the next one in the chain as well. One cable brings the power in, and one cable continues it to the next outlet. For the purpose of replacing the outlet, it doesn't matter which cable is which. Just be sure to reconnect the wires the same as you found them. The incoming and outgoing ground wires must be spliced together with a pigtail to the ground screw of the outlet. The black and white wires attached to their appropriate push connectors. The standard outlet that we see at home is actually called a duplex outlet. Duplex because there are 2 plug-in points, 2 outlets, one on top and one on the bottom, brought together as a single device. There is a brass connector that connects the duplex outlets together. Therefore, there is a push connector for each outlet, one for the top and one for the bottom. In our example, it doesn't matter which cable connects to the top outlet, incoming or outgoing, as long as one does and the other cable to the bottom outlet, as seen here. This allows the power and ground to be continued to the next outlet in the chain. And that brings up something else to be aware of, the split outlet. This is a convenient way to turn on a room lamp in the evening without having to enter the room and find it in the dark. Commonly used in bedrooms. Here is a diagram of how that's wired up. In this example, the power comes in at the top of the wall switch junction from the service panel breaker. The second cable, which in this example exits on the right, runs to the outlet junction box. The wiring is as follows. The green ground wire from the service panel is spliced to the green wire going to the outlet, along with a pigtail connection to the ground screw of the switch. The white neutral from the service panel is spliced to the outgoing neutral to the outlet. Now the incoming black wire is spliced to the outgoing black wire with a pigtail connection to the first screw on the switch. The red wire from the outbound cable is connected to the second screw on the switch. The result is that the black wire going to the outlet will have standing continuous power, and the red wire going to the outlet will only have power when the switch is in the on position. Before connecting the wires in the split outlet junction box, you need to create the split outlet. Do that by breaking the bridging clip that connects the two outlets together on the hot side of the outlet. Take your long-nosed pliers and bend the bridge point back and forth to break it free. This will separate the electrical path, creating two outlets. It is not necessary to break the neutral side bridge clip, but if you decide to, or if you do so by mistake, the wiring pattern shown will create a continuous neutral connection to all outlets. In this example, there are 3 splices along with an outgoing cable at the bottom right, which feeds continuous power to the next outlet down the line. The ground wires are spliced together with a connection to the ground screw on the outlet. The incoming neutral white wire is spliced to the outgoing white wire with a connection to the neutral of both the top and bottom outlets. Now for the power split. The incoming black is spliced together with the outgoing black with a pigtail connection to the bottom hot screw of the outlet. The incoming red wire is connected to the top hot screw of the outlet. This creates the switched split outlet. The top outlet operates with the wall switch, and the bottom outlet has continuous power. We're coming to the end of this series, and the final thing you need to know is what to do and what not to do when the power goes out. Depending upon where you live, you may experience power outages on a predictable basis. From hurricanes to tornadoes, to ice storms, to rolling blackouts, to the drunk driver taking out a utility pole. It may happen all the time. The reasons vary. And when this does happen, the path many take is to fire up a portable generator until the utility company can restore full power. Portable generators can be quite beneficial to keeping your critical items working in the house. It's how you bring that generator into service that requires planning and consideration. And there are rules to follow. First and foremost, just as a reminder, the generator produces carbon monoxide when it operates. It must be kept at a minimum 5 feet away from the house and operated in the open. Don't place it under a window or just outside the door to the house. Never in the house or in the garage or the basement. Never. Always outside, in the clear, in the open. Many people run extension cords through a window or door from the generator. They want to plug in the refrigerator, the TV, the computer, and the microwave. It may be a window air conditioner or electric heater. This is fine, as long as you have a carbon monoxide alarm in the house. It can be battery operated or plugged into the power. Remember, keep the generator far enough away to prevent carbon monoxide from entering the home. With that spoken to, next up is the extension cord, and I'm going to spend a little time with this. When we're talking about a generator and extension cords, the terminology changes from volts to watts. Watts is the term given to represent power, just as ohms is the term given for electrical resistance, and volts for electrical pressure. Amp remains the term for the amount of electricity. When talking about a generator's capacity, we're talking about the amount of power it can make, and that's measured in watts. In general, generators are identified by the starting watts and running watts. Starting watts is that high power demand a motor needs to start turning. Running watts is the amount of continuous power the motor needs to keep running. The two are different. In this example, the generator can produce 4,000 watts of power at its best. That's the peak power, but only for a short duration. The normal running watts are only 3,500. However, regardless of how many watts the generator may supply, if you're using extension cords, there are practical limits as to what you can power up, and those limits may be different from what you see printed on the package the cord came in. The two things you need to understand when it comes to extension cords is how many watts of power the cord can support and how many watts of power the appliance or appliances require. And this applies whether you're plugging the cord into the generator or the wall outlet. To determine appliance wattage, check the information sticker on the appliance. It will state its electrical needs. This will either be the voltage and watts or the voltage and amps. If it only provides voltage and amps, then calculate the watts by multiplying the voltage by amps. For example, if the sticker reads 120 VAC 3A, that's 120 volts of alternating current and 3 amps. Multiply 120 by 3, which equals 360. 360 watts is the true power requirement. The typical 50-foot extension cord you purchased at the hardware store, which uses a number 14 gauge wire, will support 1,440 watts of power under a steady draw. The next higher rated 50-foot cord, which uses a number 12 gauge wire, will support up to 1,920 watts under a steady draw. Wire gauge and length of the cord make a difference as well. The smaller the physical wire, such as a 16 gauge, the fewer watts it can handle. And the longer the cord, the fewer watts it can handle. The 1,440 watt capacity of a 50-foot cord drops to 1,200 watts in a 100-foot cord, even though it's number 14 gauge wire. It's important to understand this and not rely solely upon the printed capacities on the package. What's stated on the package is the absolute maximum for that cord. In this example, the cord is rated at 15 amps and 125 volts. Multiply those two numbers together and it looks like the cord can support 1,875 watts. Technically, maybe. Practically, no. First, the standard electrical rate from either the utility company or your generator is 120 volts, not 125. 125 is the maximum voltage the cord can take without damage. Second, 15 amps is the maximum that a 14 gauge wire can handle. If you pull a continuous 15 amps through a circuit, the wire will get hot and the thermal breaker will trip. Wall outlet or extension cord, the limits are the same. Gauge and length determine those limits. The normal continuous draw through a 14 gauge wire is 12 amps. Back to our example, the packaging is correctly stated but misleading. It touts how much it can do when in reality it's going to be less than that. 120 volts multiplied by 12 amps is 1,440 watts. Under normal conditions, that's what the cord can safely handle. As you connect up your appliances, do not exceed the wattage rating or the cord will heat and could possibly catch fire. Here is a short list of common items and their estimated wattage requirements. Your appliances may vary. If your generator provides 7,000 watts of running power, you may need to pick and choose the critical items that need to be powered up given the limits of the extension cords you're going to use. It's a lot to take in and it can be confusing, but with a little planning and compromise, you'll be ready for the next power outage. I said there were do's and don'ts when it comes to using a portable generator at home. Here is a major don't. Do not plug the extension cord from the generator into the wall outlet of the house. You see stuff like this promoted on the internet suggesting you can power the entire house with one single cord. Will it work? Not exactly as their videos suggest, but to a degree, perhaps. But don't do it. It's illegal in most locations, and not only that, it's dangerous. Maybe not to you, but it will be to anyone working to restore utility power, even deadly. Remember, electricity wants to travel through any wire connected to it. Any wire, including the utility wires to your house. It's called backfeed, and that's a serious danger. Here's a scenario. A car hits a utility pole down the road and knocks out power. You roll out that backup generator and plug it into the wall outlet of the house. That electricity will flow into the house circuits through the common hot bus in the service panel. But it will also travel from the service panel to the utility wires, reaching the transformer on the utility pole. The electricity coming from the wrong direction will be stepped up by the transformer from 120 volts to 7,000 volts. That will be sent down the transmission lines. It could electrocute the utility person working a mile down the road trying to get the power back in service. Truly a dangerous situation, one for which you could be held criminally liable. You don't want to hurt anyone. Never do this. There are ways to connect the generator to your house wiring safely without endangering others. Most locations require a transfer switch for the generator to be directly connected. The transfer switch is an isolation reroute of the branch circuit, allowing electricity to feed into the branch either from the utility service or from your generator. These devices can transfer the source automatically, or it can be manually transferred. During the power outage, when the generator is employed, the transfer switch will energize selected circuits, isolating them from the utility lines, preventing backfeed. And with that, we'll conclude this video and this season's series. I hope you found it helpful with understanding electricity. I certainly appreciate you watching. Thank you very much.